All right, so hello, and welcome everybody on this beautiful platform PW. This is your physics mentor Gaurav Tiwari, and today, my dear kids, we are going to talk about the chapter called as gravitation, right? But before we start with anything, first let me know if I'm clearly audible and visible or not. Hello, everybody. Right. Just quickly tell me if I'm clearly audible and visible or not. Hello, everybody. Okay. All right. Okay, so let us wait for a minute or two and allow everybody to join. My dear kids, if you are in grade 11th and you are moving to grade 12th, this is going to be another important session for you, right? Certain concepts of grade 11th are like, universal, right? They help you, to connect the dots everywhere, right? Like there are certain numericals, some good numericals in the grade 12 physics where you need the concepts of grade 11th, right? So that you can solve them completely, right? So the concepts and everything we'll be discussing today, right? But before we start with anything, let me know if I'm clearly audible and visible or not. Hello everybody. आवाज आ रही है सबको कि नहीं? Hello everybody. कैसे हो तुम लोग? Hello everybody. All right. Okay. तो बहुत सारी बातें आज होने वाली हैं. We will talk about so many things in this chapter of gravitation, right? We'll be discussing so many things about the chapter of gravitation, right? जल्दी से बताओ मेरी आवाज आ रही है आप लोगों को नहीं आ रही है? Yes, hello Raj. Yes sir, English में समझ नहीं आएगा. Okay, but this channel is in English, right? So you have to stick to the language of the channel, right? I can speak Hindi as well, but there are other, there are certain rules that why we have created this channel, right? So again, we have to stick to this language, right? So let us continue, right? So here it is. So you see that this is your moon, right? And something weird is happening over the moon, right? You see that when you look at the surface of the moon from the surface of Earth, you see when the guy is walking on the moon, he can jump fairly higher, right? You see that when an astronaut is trying to jump on the surface of moon, he can jump fairly, higher as compared to the surface of Earth, right? You see, when he tries to jump, he can jump much higher, right? So why is that happening? The reason is because of, the pull, the astronaut, the pull that is felt by the astronaut on the surface of moon is lot lesser as compared to the pull that he feels on the surface of Earth, right? We can say that the gravity of moon is lesser than the gravity of Earth, right? We will talk about that. What is the factor that controls the gravity on moon? And we will see that why is higher on Earth and why is it lesser on moon, right? So all those things we'll be discussing today, right? So let's continue and keep on talking about various interesting concepts, right? So a lot of other things are going to happen, right? So here you have another planet called Mars. So as you jump on the Mars, right, you see that you can take a longer jump and you just come back like this, right? So here you see that on the surface of Mars, you can almost jump for 1.2 meters, 1.2 meters till here on almost, right? So you can easily jump till my shoulder, right? So yeah, fairly larger jump, right? And if you take a jump on the surface of moon, right? So here it is, you see this one, right? Here you can take a fairly larger jump. So the number is not visible. It is around 2 meters or so, right? So 2-3 meters, you can take a jump very easily, right? So yeah. So now all of that is happening because of variation in the value of gravity. And why is that value changing? We will talk about that in this session, right? Here we have it. Now, in the early part of development of science, we used to believe that the God has created the world, like not us, the people who were like religious of certain section at that time, right? They used to believe, especially in the European countries, there was a rule of church back then, and as per their norms, right, they used to think that the God has created the entire universe for us, right? So the earth is at the center and the world is revolving around us. And that is why we said that the sun is rising from one side and it is setting on the other side, right? So this kind of model was was the geocentric model, right? Geo means the earth and centric means the earth is at the center and sun and moon and everything else is around it, right? Later on, there were a lot of people who tried to deny it. They got the really good punishments for that as well. So the first guy in the line was Copernicus, right? What Copernicus said that, like in the Europe, Copernicus was the first, but in India, you know that we already knew way before that the Earth is not at the center; it is the sun which is at the center. But the Copernicus came up with this idea that is well documented, that it is the sun which is at the center, and all other planets are moving around it, right? So a lot of things happened in that line of action, right? And then Newton was sitting in a tree, and one day he got struck by an apple, very famous story, and that's how the laws of gravitation came into the picture, right? So there are a lot of dots that we have to connect so that we can study this chapter, right? So a lot of dots we have to connect, and we will talk about each of those dots, right? We will talk about all those stories. We will talk about a lot of details in this session, right? So a lot of learning is going to happen in this particular session, right? So if you guys are with me, we can start right away. Just give me a quick yes, and this is going to be the starting point of this class, right? Okay. This is going to be the starting point of this class, right? So let's start right away. The first thing is Newton's law of gravitation. My dear kids, we used to believe that the earth has a supernatural power due to which the earth attracts the objects towards itself, right? Everything falls towards the surface of earth, right? We said that the earth has a very important and a specific feature, but Newton said that it is not the specific feature of earth, right? It is the feature of every single thing that has mass, right? So everything in the universe that has mass attracts every other object in the universe that has mass, right? So any two objects having the masses m1 and m2, they are separated by a distance r, are going to apply a force on each other. The name of this force is force of gravitation. Is that clear? Any two objects in the world, any two objects in the universe that have a mass will apply a force on each other, and the name of this force is the gravitational force. I hope the idea is very, very clear. My dear kids, the force that these objects are going to apply on each other is proportional. The force that these guys are applying, the objects are applying on each other, is proportional to the product of masses. So if the masses are higher, the force between them is also going to be larger, right? And this force is also inversely proportional to a square of distance between them. So what is happening? If you increase the distance, what will happen? The value of force between them will reduce, right? If you increase the distance between them, the value of force between them will reduce, right? Raja Babu Mathura. I know, my dear kid, you cannot understand English, but you can watch on other channels of PW. There are all other channels in the languages you like, right? आप कोई भी चैनल पे पढ़ सकते हो बेटा जिस पे आपको समझ में आता हो. So that is for you, right? But for this particular channel, we have to stick with English. That is why the name of the channel is PW English, right? So here it is. So if you join them up, F is proportional to m1 m2 upon r square, right? And this is what we have written over here, right? F is proportional to m1 m2 upon r square, like this, right? F is proportional to m1, F is proportional to m2, and it is inversely proportional to square of the distance. So if you keep on moving them apart, the value of force will reduce, right? So clearly, if the proportionality sign is removed and we have to use the equals to sign, a constant will come into the picture, and that constant is a universal constant, right? There are not many universal constant in physics. This is called as universal constant of gravitation. It is F equals to G times m1 m2 over r square. F equals to G times m1 m2 over r square. I hope it is making some sense, right? Very good. Very good. Very good, Satyam. Okay. Alright. So F is equals to G times m1 m2 over r square. This is the Newton's law. I hope the idea is very, very clear, right? Okay. Just a second. Alright. So let's keep on moving in the forward direction. If, my dear kids, you know the Coulomb's law, right? You are going to move into grade 12th, right? There you are going to study the Coulomb's law, right? And here we are trying to understand the interaction between two masses and the interaction between two charged particles is pretty much same, right? You see that here we have two masses. These two masses are going to attract each other, right? If we have two charges, positive charge and a negative charge, they are also attracting each other. And the value of force that is going to act between these two charges is proportional to their individual charges Q1 and Q2, and it will reduce if you move them apart. So F is inversely proportional to 1 over r square. Kind of similar to that, right? Instead of mass, here we are using charge, right? So the way those two masses interact with each other is pretty much same as compared to the way those two charges interact with each other, right? So this is the gravitational force. You will find that lot of interactions between two masses is similar with the interaction between two charges, right? So we are going to talk about that as we move ahead, right? So this is a very common comparison between these two things, right? Okay. Now let's move on and talk about the next idea. Okay, so the numerical value of universal gravitational constant is determined by a Cavendish experiment in 1798. So you don't have to remember the year, but just for the sake of remembering things, the Cavendish experiment is the name of experiment that we used to determine the value of the value of capital G, the value of universal constant of gravitation between two objects. It is 6.67 10 to the power negative 11, right? The value of G is calculated by Cavendish experiment. It is 6.67 10 to the power negative 11, right? This, okay. All right, so let's move on and talk about the next idea. So now we know that, my dear kids, that the force between two objects is a vector quantity. Yes or no? We know that, my dear kids, universe, it will be around 2 hours long, you say, 2 to 3 hours, right? But we will cover everything in gravitation, right? From initial part of the universal law of gravitation till the planets moving around the earth and sun, right? All of that will be covered. So here we have it. We want to represent the force acting between them in the vector format, right? Because the gravitational force acting between them is a vector quantity, right? The force is a vector quantity or a scalar quantity. The gravitational force between them is a vector quantity. The gravitational force between them is a vector quantity, right? And if you want to write down the vector quantity, how can you write it, my dear kids, right? If you want to write down the vector quantity, how can you write it down? Okay. Clearly, we can say that all you need to know is simply, if you want to write down anything in a vector format, just for the sake of learning things, if you want to write down anything in the vector format, for example, there is a vector, this vector, right? And in the direction of vector, the unit vector is a cap, right? How will you write down the a vector? A vector will be the magnitude of a vector. Just measure it. The magnitude of a vector is this, right? Magnitude of a vector into unit vector in the direction of this thing, okay? So if you multiply the magnitude of a vector with the unit vector in its own direction, you will get the complete vector format, right? If you multiply a vector, for example, let's say that Rishabh is moving towards x-axis. Rishabh is moving from the origin along the x-axis, and he moves 10 meters along x-axis. He is moving 10 meters along x-axis, right? So the magnitude is 10 meters. If I multiply the magnitude with the unit vector in this direction, what is the unit vector along x-axis? I cap. If I multiply the magnitude with the unit vector in the same direction, I have represented the displacement vector. So what is displacement vector? The magnitude, which is 10 meters, into unit vector in this direction, which is I cap. So any vector I want to represent, this vector, so I will multiply the magnitude of this thing into the unit vector in this direction. I hope the idea is making sense, right? Okay. All right, so let's keep on moving. Okay, let's keep on moving in this part, right? So what is really happening? F12 is F2, F21. What does that tell you? Whatever force is applied by this object on the other one, same force is applied by the other object on the first one. So you see that if the box is being pulled by the force of 1 Newton or 5 Newton towards Earth, right? The Earth is also pulled towards the box by the same 5 Newton. Earth is applying the force on the box in the downward direction, which is 5 Newton. And the equal amount of force is applied by the box on the Earth, 5 Newton in the upward direction. Both of them are applying the same force on each other, right? I hope that is very, very clear, because force is a result of interaction, right? Force is a result of interaction between two bodies. Force is a result of interaction between two bodies, right? If two bodies are interacting with each other, whatever force is applied by this on the first one, same force is applied by the first one on the other body, right? I hope it is making some sense, right? Let's keep on moving, right? So the value of force is g m1 m2 over r square, right, into r cap, right? So just r cap is the unit vector in the direction of this r vector, right? Just multiply the magnitude we already know. Once you multiply the magnitude with the unit vector in this direction, you can write down the whole thing in a vector format. You can write down the whole thing in a vector format. So that's how you write it. Okay. All right. So properties of gravitational force. First is, this is a central force. What do you mean by central force? Because it acts, let's say this is one planet, this is another planet. The central force is something that acts along the line joining the centers. This is one center, this is another center. The central force acts along the line joining the centers, right? I hope it is very clear. Yes or no? Yes. So the central force is something that acts along the line joining the center. So the gravitational force is acting along the line joining the centers, right? So it is always attractive in nature. My dear kids, between two charges or between two magnets, we can have attractive forces and we can also have repulsive forces, right? But between two masses, if you have one mass, which is this object, and if you have another mass, let's say this object, between two masses, we can only have attractive forces. Gravitational force is always attractive by nature, right? So the next thing, it is always generated as an action reaction pair, right? So like most other forces, like every other force, this force is also action reaction pair. So whatever force is applied by this object on the first one, same force is applied by this object on the other one, right? So action reaction pair. It is independent of medium. So whatever medium we have in between them, the value of force is always going to be the same, right? So if you have two masses, the value of force between them, that gravitational force is always going to be same, right? It will not change. Okay. It is independent of medium, right? It is conservative force. Conservative force means work done in this particular field or work done by this force is independent of path. Work done by gravitational force is not going to be dependent on path. For example, here I have a body and I'm moving the body from this point A to a point B. Point A to point B. Some work is done by the gravitational force, let's say in this situation, right? So if I'm moving it along this path, or I'm moving it along this path and moving to the same point. So till the starting point and the end point are same, right? We can say that the work done is same in this path as well as in the other path, right? So work done by the gravitational force, which is the conservative force, is path independent, okay? All right. So now the next thing is principle of superposition. What do you mean by principle of superposition? My dear kids, it is possible that we have multiple masses interacting with each other. So you see that, imagine right now you can think in this way. This is a ceiling. From the ceiling I am hanging a mass. Right now only this mass is pulling that particular ceiling right in the downward direction, right? I can attach one more mass and now both the masses are pulling the ceiling downward, right? So the effect of both of these things is acting over here, right? Yes or no? Now similarly, if I have multiple masses like this, m1, m2. So right now, let's say that imagine we have these two masses only, m1 and m2. So right now only these two are applying force on each other. But if I have another mass, m0 and so on, m3, m4, m5, m6 like that into the picture. So all the masses, every pair of mass is interacting with each other. Every pair of mass is applying force on each other, because universal law of gravitation said that any two masses in the universe will apply the force on each other. Any two masses in the universe will apply the force on each other, right? Okay. Yes. Okay. All right. Krish is saying something, but I believe it is so out of context. Okay, no problem. So here you see that this m1 is attracting this mass, right? Okay. But m1 is also interacting with this mass, right? m1 is also interacting with this mass. Let's take another color. m1 is also interacting with this mass like this, right? m1 is also interacting with this mass like this, right? So you see that This is the force on M1 by M2. Force on M1 by M2. This is the force by M1 by Mn. M1 by Mn. Here this is the force by on M1 by M naught. 0, right? So what is the net force on M1? We can say that the net force on M1 is net force on M1 is equals to force on M1 by M2, force on M1 by 2, right? So plus force on M1 by nth object, right? And similarly force on M1 by the M naught object. All right. So all those forces must be added vectorially, right? Superposition means when one thing superimpose over the other, like that, right? So here you see that the forces acting on this one object are superimposing one over the other, are stacking one over the other, right? So the net force is simply adding up in a vector format like this, right? The net force is acting up like this. The human also apply the forces on each other. Of course, Satyam, right? The human also apply the forces on each other, right? But if the mass is less, like 60 kilograms, 70 kilograms, 100 kilograms, then the value of the gravitational force is negligible, right? The value of the gravitational force between the smaller objects, practical objects that you see, is negligible, right? But between the planets are huge, very heavy, right? So between the planets, the force is appreciable. Okay. All right. So this is the net force. Okay. So this object is experiencing force by multiple other objects. The net force on this object is going to be the vector addition of all these things. So here we have the gravitation, right? So here I believe this part is very, very clear that if we have two objects, right, of any mass m1 and m2, they are separated by a certain distance r in the space. Doesn't matter what we have in between them, the value of force is going to be gm1 m2 by r square. This is the magnitude of force, right? Okay. Now here is our Newton chacha, right, sitting under the apple tree when the apple tree is falling over the head maybe. So he's thinking about what is happening, why is this happening. So he's thought about the earth gravity, right? He is talking about the earth gravity now, right? You see that this object is falling, right? And now you see it's a very funny thing. This object is much lighter compared to the other object, right? So now you see that if we have a bigger object, right, and as you know, the value of gravitational force is higher if the object is heavier, right? You have seen it now. F is proportional to m1 and F is proportional to m2, right? If the masses are higher, the gravitational force is also higher. So on this very large building, tall buildings, there are two masses m1 and m2, right? And they are trying to move towards the earth, right? So think about it, this mass is higher. So the earth will apply more force on this one or less force on this one. Think about it. Both the objects are trying to fall towards the earth. Object number 1 and object number 2, which object will feel a higher force? Which object will feel a higher force? We can say that the second object ideally should feel a higher force. Now think about it. If one object is feeling a higher force, one object is experiencing a higher force, it should move faster, right? But very non-intuitively, when we allowed them to fall, you see that heavier object and lighter object we are allowing them to fall, both of them reach the surface at the same time, right? A heavier object and a lighter object, both of them are allowed to fall towards the surface of earth, and we observed it that both of them reach on the surface at the same time. So why is that happening, right? Both of them are reaching by 10 seconds or so, right? So why is that happening? The heavier object is experiencing more force. Yes, it is true. But why does it take same time to travel to earth? Think about it. So here something must be same for both these objects, right? So what is this? There was a guy named Galileo. He did this experiment, right? Like people say that he, climbed up all the way on the top of this building called Pisa, the Leaning Tower of Pisa, and he started throwing things from it, right? Lighter things and heavier things, and he observed that all those things reached at the surface on the same time, right? So how is that happening? It was very counterintuitive because Newton already established, and it was already correct, that the force experienced by the gravity due to the gravity is higher if the mass is higher. right? So how come the heavier object comes at the same time with a lighter object? It should come much far faster, right? Why is that happening, right? Why is that happening? So let's talk about that, right? Now, over here I can explain, just a second. Yeah, over here I can explain. Now think about it. Let's say there is a ratio A upon B, okay? There is a ratio A upon B. If I increase the A by 2 times and I also increase the B by 2 times, right? If I increase A by 2 times and I also increase B by 2 times, right? So then what will happen? Will there be any change in the ratio? We can say no. We are multiplying both things by the same number and there will be no change in the ratio. If I make increase A and B by the same amount, the ratio will not change. This is our common sense, right? Now you see that here is a heavier object and here is a lighter object, right? Both of them are moving towards the earth. Clearly, the heavier object is going to experience more force, but force experienced per unit mass, the mass of this object is, let's say, capital M or M1, let us say, right? So force experienced by M1 is this ratio, and it is experiencing a force, let's say F1, which is larger, right? Okay. And the lighter object is going to experience lesser force, so F2 is smaller, and mass M2 is also smaller. So the ratio of F2 upon M2 is here, right? Now if you observe force upon mass, here this force is higher on a bigger mass, but the mass is also larger. So big thing upon big thing, right? We have a ratio of big thing upon big thing. And here we have the force which is smaller because the mass, because the object is lighter, right? But M2 is also smaller, right? So we have a big thing upon big thing. Here we have the small thing upon a small thing. And the ratio is coming out to be the same. The force upon mass acting on the body is acceleration. So we found that the acceleration of this heavier object and the acceleration of the lighter object is same, right? The acceleration of the heavier and lighter object is same. So why is that happening? Why the larger force is not creating higher acceleration? The reason is because the force is larger, but the mass is also larger. So both the things are increasing. If the force is 10 times higher, the mass is also 10 times higher, right? So 10 and 10, same thing is multiplied in the numerator and denominator. The ratio will not change. The ratio will remain same, right? So both the objects will experience exactly same acceleration. I hope the idea is very, very clear. Okay. Now this is Earth's gravity, right? So the value of G, the universal constant, is this. Mass of Earth is 6 × 10⁻24 kilogram, and radius of Earth is 6400 kilometers or 6.4 × 10⁻6 meters, right? So what is really happening over here? So if there is an object M, right, and there is this Earth, mass of the Earth is ME, right? The diameter of Earth is 2 times the radius of Earth, right? So what will be the acceleration due to gravity on the surface of Earth? So my dear kids, the force between this mass and the Earth that will act by the Newton's law of gravitation is Gmem upon Re square, right? Now you know that the force acting on this object which will act towards the center of Earth is the weight. You call it weight. What is the definition of weight? My dear kid, the weight of any object is the force by which the object is pulled towards the Earth. What is the weight of this ball? Weight of this ball is the value of force by which this ball is attracted towards the Earth, right? So clearly we can say that the weight of this thing is m into g, right? M into g is acceleration due to gravity, right? So this force must be m into g. This force is m into g, right? And when you equate them, this m and m, the mass of the object, cancels out from both sides, and the value of gravitational force on Earth, the gravitational acceleration on Earth, comes out to be this value, right? Here you see that this capital G is a constant, universal constant of gravitation. Mass of Earth is a constant, right? And also the radius of Earth is another constant. So all these three things are constant, yes or no? The value of G, ME and RE, these are all things are almost constant, we can say. The value of G, acceleration due to gravity on the surface of Earth, is not dependent on the mass of the object, right? If it was a smaller object or a heavier object, it will have the same acceleration due to gravity. I hope it is making some sense, right? Any problem in this part, right? I hope this is very, very clear to all of you. right? And if you have any other question, you can definitely ask me. All right. So let's continue to move on and talk about the next part. So comparison between GE and GM, right? So now we can talk about why the guy was jumping much higher on the surface of moon as compared to the surface of earth, right? You see, so the value of G is 6.67 10 to the power negative 11, and mass of moon is 1/100th of mass of earth, and radius of moon is 1/4 of radius of earth, right? Okay, so these are the things we know, right? Mass of moon, we know that it is 1/100th of mass of earth, and radius of moon is 1/4 of radius of earth. And following that idea, if we try to find the value of force right now on the moon, what will be the value? This is the mass of moon, this is the diameter of moon, right? And right now if we try to find out the values, what will be the value, my dear kids? Right? You see that here, this is the value of small g on the surface of earth, right? Now, similarly, in place of mass of earth, if you put mass of moon, right? And in place of radius of earth, you put radius of moon, right? You will get the same thing, acceleration due to gravity, but for the moon, right? Okay. Now you take the ratio of these two things, gm upon ge. What will you get? Gm upon ge will be the ratio of these two things, and it comes out to be 1/6. So what do you learn from this idea? We can learn one very specific thing from this particular thing, that the acceleration due to gravity on moon is 1/6 of acceleration due to gravity on earth. That means the pull you experience towards earth right now is 6 times more than the pull you will experience over there, right? So if you are jumping for 1/3 of a meter over here, you will jump 6 times more, that is 2 meters around over there. If you are jumping 1 meter over here, you will jump for 6 meters over there. So whatever you are jumping here, you will jump 6 times more, right? So it is a reasonable change. I hope the idea is very, very clear. Okay. All right. So let's continue to keep on moving forward. So here we have it. So this is now the value of acceleration due to gravity. Is it constant everywhere? My dear kids, capital G, the universal constant of gravitation, that is constant everywhere, right? But what about this thing? What about this small g? What about this acceleration due to gravity? Is this value constant everywhere? So my dear kids, I will tell you that this is not constant everywhere. There are various reasons that will change the value of acceleration due to gravity on any other planet, right? For example, Earth, right? So you see that the first reason due to which the acceleration due to gravity will change is with the height from the surface, right? So if the height from the surface changes, the acceleration due to gravity will change, right? If you dig deeper, right, and you come over here at the depth d, right, the value of acceleration due to gravity will change with the depth, right? And here, due to the rotation of Earth, now you may have seen as anything rotates, right, it has a tendency to break the rope, right, by some forces. We will talk about those things as well. So with the help of rotation, because the Earth is rotating about its own axis, there is a variation in the value of g. The value of g you get over here is not same as the value of g you get over here, right? Because the distance from the axis of rotation is different everywhere, right? And the next thing is shape of Earth. The shape of Earth also affects the value of acceleration due to gravity, because the Earth is much like a flat orange, right, instead of a round sphere. So pretty much the value of g is different across this axis as compared to this axis. I hope the idea is very, very clear. So there are various factors that will affect, that will change the value of small g. That will change the value of small g. Clear? So my dear kids, the capital G is universal constant of gravitation. It is same everywhere. But the small g is the acceleration due to gravity. It is not same everywhere. It will change with the places, right? Okay. So this is the first explanation. How does the value of small g changes with height, right? So if you are moving with height h, if you are moving at a height h, what will be the new value of acceleration due to gravity? Let us learn that, right? What will be the new value of the acceleration to gravity? So my dear kids, here you know that, let us say the value of acceleration due to gravity over here at the height h from the surface is GE dash, right? Value of acceleration due to gravity over here at the height h from the surface is GE dash. My dear kids, right now at this particular point, let's say here we have a mass m, right? This is the center of earth. Clearly the radius of earth is RE, okay? So what will be the total distance from the object? So RE plus h, yes or no? So total distance is going to be RE plus h. So what will be the new force? We can say the new force will be GMEM upon this entire distance squared. So RE plus h squared, right? So let's call this distance as R dash. R dash is going to be RE plus h. Yes or no? RE plus h, right? So right now you see that the new force, which is m into GE dash, right? We, of course, you know that the value of G over here is G dash. So how much force will be acting over here? We can call it m into G. The new value of G is G dash. mGE dash is acting downward. So the new force over here is this much, which should be equals to GMEM upon new distance squared, R dash squared, right? Okay. So now you can put the value of R dash, which is RE plus h, right? And you can further solve it. So as you put the value of RE, as you put the value of R dash, right? And you can take the RE square common out of it, the new value of GE dash you can get is this. So G upon 1 plus h upon RE whole square. G upon 1 plus h upon RE whole square. So if let's say that you are moving away from the surface of earth, right, at a distance h that is also equals to the radius of earth. Let us say that here the radius of earth is around 6400 kilometers and you move away from the surface of earth again for another 6400 kilometers. What will be the new value of G over here? So this is the question, right? If the h is equals to RE, what will be the new value of G over here? Right? If you move towards a place, this is the surface of earth, right? And the radius of earth is 6400 kilometers. From the surface, you are moving to a place which is also equals to the radius of earth. What will be the new value of G over there? So my dear kids, h is measured from the surface, right? And that is equals to RE. So the new value of G dash is equals to, right, GE upon 1 plus h upon RE. So which is RE upon RE ka whole square. So we have this thing, RE upon RE is 1. So GE upon 1 plus 1 is 2. So GE upon 4. So you see that the value of acceleration due to gravity will be 1/4 if you move away from the earth for a distance which is equals to the 6400 kilometers or the radius of earth, right? So that's how the value of this thing change, right? Okay. Walter White. Thank you, beta. All right. So let's continue to move. So now this is the first variation in the value of G, okay? G dash is G1 plus h upon RE whole square, right? Okay, so what is this thing? Understand that. This is again a very, very important formula. So my dear kids, at a height h, the new value of G is written this GE 1 minus 2h upon RE. But sir, in the previous page you taught us that the value of G is this. The new value of G over here, the acceleration to gravity over here is this G upon 1 plus h upon RE whole square. And right now you are telling us it is 1 minus 2h upon RE. Why these two formulas are different and telling us the same thing, which is the value of G over here, right? If these two formulas are telling us the same thing, the value of G over here, why are they different? My dear kids, we have just simplified it into this form, and this is only applicable in a very specific situation. When? My dear kids, if you are moving away from the surface of earth but you are not moving too far, let's say the radius of earth is 6400 kilometers, the radius of earth is 6400 kilometers, and you move away from the surface of earth for a very, very small distance, for example, you throw a ball, right? So the ball will move up by 50 meters, 100 meters maybe, right? So you see that the height 100 meter is negligible as compared to 6400 kilometers, right? So you see that if the height of the object is very small as compared to the radius of earth, only in those cases we can simplify it and write it in this way. That is called as this binomial expansion. So what is really happening? 1 plus x to the power n, right? It becomes 1 plus power becomes coefficient if x is very small as compared to 1, right? If x is very small as compared to 1, then the power will become coefficient, it will become 1 plus nx, right? So here you can see that if the height is very small, if the height from the surface of earth is very small, let's say 1 kilometer, so h is 1 kilometer and radius of earth is 6400 kilometers. So clearly this thing which is added to 1 is very less as compared to 1. If whatever is added to 1 is very small as compared to 1, so what will happen? The power will become coefficient. The power is becoming coefficient. The power is becoming coefficient, right? So what is happening? The power is going to become coefficient, right? So this power, if you take the whole thing up, the power will become -2, right? The whole thing up, the power will become -2. The same thing is written over here, and the power will become coefficient. So -2 is coming over here. This is the new value. So my dear kids, this formula is valid for all the heights. This formula is valid for all the height from the surface of earth. And this formula is valid only when the object is very close to the surface of earth. I hope it is making some sense, right? Any problem in that part? I believe the difference between these two formulas and how are you going to apply them is very clear, right? So now let us keep on moving and talk about the next part, okay? Right. Now, the next possibility in the variation is when you dig, right? Now think about it. When the object is on the surface of earth, the entire earth is pulling, the mass of entire earth is pulling the object toward itself, right? When this is the object and this is the earth and the object is placed on the surface of earth, right now the entire mass of earth is pulling the object toward itself. But if you dig a well in it, right, and now the object is over here, so you see that only the remaining portion, this portion is pulling the object toward its center, and the object and the part of the earth which is outside has nothing to do with it. Yes or no? You see that again. So you see, right now the object is at the surface, entire earth is pulling it, but when the object falls right over here, so right now only this portion is pulling the object towards the earth, and the remaining portion which is outside is not pulling towards the center, right? So now you see that the effective mass which is pulling the object is reduced, right? Previously the entire earth was pulling the object, and now only this portion of the earth where the object fell to, right? The object is now here now. So only the remaining portion of the earth, which is this, is pulling the earth. Now the attracting portion, the mass of the portion which is attracting is reduced, right? So now it will apply lesser pulling force. Now it will apply lesser pulling force, right? Okay. So what will be the mass density? So my dear kids, the mass density will be me upon 4/3 pi r cube. So this is the mass per unit volume, right? So here you can see that for the entire earth, the radius is re, the mass is me. So what will be the mass density? The mass density will be mass per unit volume. All right. The mass density will be mass per unit volume. I hope the idea is very clear, right? Okay. So let's keep on moving. All right. Okay. So m into g dash is this thing. So right now, when the object is at a much lesser distance, right? When the object is over here, so this is the effective earth you have, right? So we are not talking about the entire earth. We are only talking about this earth, right? That has lesser mass, me minus m dash, right? So the new mass is this, right? So the new mass is this m dash, right? Okay. And we are reaching over here, right? So now think about it. Think about it. If the entire thing, let's say you are digging for the height h, right? If you're digging for the height h and the total distance was re. So basically what will be the new radius? It is re minus h, right? So no? So r equals to re minus h basically, right? Okay. So here it is. So just put the value, the new force of attraction mg dash over there is going to be gmm dash upon r square. Okay. Now if you put the values of everything, you will get GE dash is equals to GMER upon RE cube. The new value of GE is going to be this much, right? And now you can replace the value of a small r and everything, right? So r, small r is equals to re minus h, as I said, right? So small r is equals to re minus h, you put the values, and this will be the new value of acceleration due to gravity over here, right? So at a depth h, if you are moving at a depth h, the new value of g over here is going to be GE, value of earth on value of gravitation, acceleration due to gravity on the surface of earth, right? Over here the value of gravity is earth, due to earth is GE, right? Wait a second. Over here the value of acceleration due to gravity is GE. So the effective value over here, GE dash, is GE1 minus h upon RE. I hope the idea is very, very clear, right? So this is the main idea. So there are two things, two variations that we have understood. In the first case, the object was moving away from the surface of earth. We understood that the new value of acceleration due to gravity will reduce over there. And as we dig deep, the new value will again reduce and it will achieve a new value again, right? So the new value at a depth h is equals to G1 minus h upon RE, right? The new value at the depth h will be G1 minus h upon RE. I hope it is making some sense, right? Any problem in this part? Is that clear? All right. Okay. So let's keep on moving and keep on talking about the remaining ideas. Okay. So we are here. We have discussed till this part. Right. And we have also discussed the value of G at a certain depth D, certain depth H. Yeah. So we are over here and let's continue from over here, right? Now we are going to learn what will be the variation in the value of G due to the rotation, right? What will be the variation in the value of G due to the rotation? Here, understand that, right? So to understand that specific idea, we can talk about a little, imagination part, right? So we have to imagine things a little bit, right? So imagine this object is rotating about this axis, right? This object is rotating about this axis, right? Like this. So what is going to happen? As this object rotates about this axis, what will happen? Anything which is over here will try to rise up. Anything which is over here will try to rise up. For example, when this thing is over here, right? So if I try to rotate it, you see that there is a tendency of this object in rising upward and moving out. Yes or no? So you see that similarly, this object, right? This object, right, which is placed over here, let's say that you are living in this part of the earth, you are standing over here on earth, and the earth is moving. So basically, you are moving on a circular path. You are moving on a circular path. Clear? And when the object is moving on a circular path, there is a tendency in the object to move outwards like this. So that there is a tendency that will try to, throw that object away. So like this, let me show you over here. You see that this object is moving in a circle, right? Any object is over here, it is moving in a circle like this. Any object over here on the surface is moving like this, right? Any object over here is moving in this circle. Any object over here is moving in this circle, all right? So every object which is on the surface is basically moving. As the earth rotates, the object itself rotates with it, with the earth itself, right? And it is moving on a circular path, right? Every object on the surface of earth is moving on a circular path, okay? Right? Every object on the surface of earth is moving on a circular path. And if I follow this thing, you see that from the force which is acting away from the surface of earth is mr omega square, right? Okay. Mr omega square, okay. Now you can take two components of this force, right? One, it is along the axis, and one which is this way. Now think about it. The object is experiencing a force towards the center of earth. That force is called as weight, right? The object is experiencing force towards the center. This is the center of earth. Object is experiencing a force towards the center. This is force is weight of the object. This is the weight of the object which is acting towards the center. So weight is acting in this way. Mg is acting in this way. Okay, right? So object is on the surface and the weight of the object is acting toward the center, right? And we have seen it, mr omega square is acting outward from the circle, right? Like this, okay? So we can take two component of mr omega square, one that acts along this axis, the weight axis, and the other one is like this, tangential to it. Now you can say that mg should be the actual weight, but due to the rotation of Earth, let's say the Earth is rotating at an angular velocity omega, right? So the effective force is not mg, it is mg minus mr omega square cos theta, right? Effective force is not mg, it is mg minus mr omega square cos theta. So this is the net force, mg minus mr omega square cos theta. So this is the effective force, mg minus mr omega square cos theta, and due to that the effective value of g is going to be this. All right, due to that the effective value of g is going to be this. Okay, I hope the idea is very clear, right? So due to the rotation of Earth, since the Earth is rotating at an angular velocity omega, the effective value of g reduces. Okay, the effective value of g reduces. All right, okay, so this is the another factor, right? At equator the theta will become 0, right? At equator the value of theta will become 0, and at pole the value of theta will become 90 degree. You can use the value over there, right? So at effective value of acceleration due to gravity along the equator, any point on the equator, you are standing on any point of the equator of the Earth, then the value of g you are experiencing is g minus re omega square, right? But if you stand on the pole, right, you see that something is reducing from g, right? So you see that number cos 0 is maximum, so that number is maximum, right? Here maximum value is reducing. So you see that due to the rotation of Earth, you get minimum value of acceleration due to gravity over here. But on the pole, you see that the value of theta is 90 degree. So when you put cos 90, it is cos 90 is 0. So the number which is reducing is 0, and the value of effective value is basically maximum, which is equals to the value of g, right? So this is the value that you can get on the pole, right? So the 9.8 meter per second square, generally what we say now, that we can get on the poles, right? Okay. Now the last reason that affects the value of g is the shape of Earth, right? The last reason that affects the value of g is the shape shape of Earth. Parnika is asking, sir, if you prepare from class 12th for NEET, can we crack? Of course. There are kids, they like in the past I have seen those kids as well, right? Especially like kids generally start after the grade 11th, right? Because they have just been through a board exam of grade 10th. So it's a very common thing that kids generally end up wasting their grade 11th because they are trying to recover, they are taking a rest. They forget that in the process of resting they have wasted another year, right? So generally the kids wake up during the 12th, and this is why we are taking these lectures, right? So that maybe you are watching right now, or you will watch during the recorded time, right, as a recording. So you see that these lectures will help you to recall those concepts, so that when we are going to learn, you see that here in the beginning of the chapter I told you that the gravitation is pretty much similar to electrostatics. The first chapter is electrostatics, right? So if you don't know gravitation, you won't be able to relate, right? You won't be able to relate. Huh? Sir, can JEE aspirants see this or backlog to complete this chapter? Yeah, basic concept. If the concepts are not covered, then you should watch it, right? But the basic idea of this particular lecture is not to address the JEE problem, right? The basic idea is because when we are going to teach you the grade 12 concepts, there will be a lot of hurdles that we face, right? The problems that we face is we are trying to compare gravitation with electrostatics with the first chapter, right? And kids don't know the gravitation itself because that was taught in grade 11th. So there's a gap in the grade 11th concept and 12th concepts. That is why we have this bridge, right? We are bridging it. So this is the bridge course, right? Okay. So this is the idea. Yes, Parnika, we will do that soon enough. Okay. So let's continue, right? Let's talk about the next idea. So due to the shape of Earth, again, there is a variation in the value of g. How does the value of g changes due to that? Let's talk about that as well, right? So here it is. Here, you see, this is the pole. This is the equators, right? So the diameter across pole is this 2 times radius across pole, and diameter across equator is 2 times radius across equator, right? It is not same, right? You see that the Earth is slightly flat at the top. So basically this is higher than this, right? So clearly now when we try to write down the value of g anywhere, right? Now when we try to write down the value of G anywhere, okay, so we know that the value of G is inversely related to R, right? We know that if you move away, if you move away from the surface of Earth, right, we know that if you move away from the surface of Earth, what? This is the surface of Earth, right? And here you are, right? So if you move away from the surface of Earth, the value of acceleration due to gravity reduces further, right? So now think about it. If the Earth is like this, okay, further you are, lesser the value of G you will get. So you are over here. You are much further at this place as compared to this place, right? So further you are, lesser is the value of G, right? So on equator you are much further as compared to pole, right? So where will you get higher value of G, my dear kids? Where you are closer. So on the poles you will get higher value of G. Due to rotation also you are getting higher value of G at the poles, and due to the shape of Earth also you are getting the higher value of G at the poles. So due to all the factors, the value of G that is at the poles is maximum on the Earth as compared to any other place, right? Okay. I hope that is very, very clear. Right, let's keep on moving and talk about the next part. All right. All right. So this is the idea, gravitational field. What is a gravitational field? Right. So you see that if you take a planet, right? Let's say that in a free wide space, right? There is this planet. Okay, this is this planet, right? Let's call this planet is a Mars, right? It is rotating in the free wide space, right? Now, what is really happening? Another planet is another object, let's say some random asteroid is moving, right? But it is so far away that it is not attracted by this one. But if you reduce the distance, now it is attracted, and now once the object is attracted by this particular planet, the asteroid is now taking circles around it, right? Circles around it. Okay, the same thing is happening with Earth, and the same thing is happening with different other planets, right? Okay. My dear kids, one thing we have seen that there is a point beyond which, right? There's a point beyond which these two objects don't seem to interact too much, right? We can call that this place is outside the influence of this object, right? The place beyond that, this place where it is not interacting, is outside the influence of this object, right? So the place of this object, the place around this object where I can interact with this thing, the gravitational forces of this thing, is the gravitational field of this object. So what is the gravitational field? The place around, the space around a given mass where you can interact with it, right, is the gravitational field of this particular mass, right? So clearly, higher the mass, bigger or larger will be the gravitational field. So you see that if you talk about sun is massive, right? Sun is huge. So an object which is further away from sun, right, will be attracted towards the sun, right? But the object, if it is really far away from Earth, it will not be attracted toward the Earth because Earth is lighter, right? So the gravitational field of Earth is much smaller, right? But the gravitational field of sun is much, much larger, right? So you may have heard about this thing that this is the sun, and around the sun you have 8 planets. After those 8 planets, you know, I will not get enough space. Around the sun, you have these 8 planets, right? After the 8 planets, there is a gap, right? So you know that Mercury, Venus and Earth and, you know, Mars and, you know, Jupiter and like that, right? All of the planets are there, right? Neptune and all. So, you know, and between the Mars and Jupiter, there are a lot of asteroids, right? This, you call that asteroid belt. You see that? All those things, all those asteroids are attracted towards the sun, right? They are in the gravitational field of sun. Sometimes they get, you know, deviated, okay? Right. So you see, asteroid belt is there, but this is not the only asteroid, right? After the Neptune, right? The all the objects after the Neptunes are called as trans, post Neptunian objects and all, right? So so here it is, right? Beyond the Neptune now, there was another thing called Pluto, but we don't count it as a planet anymore, but there is a Pluto, right? Beyond Pluto, there is another belt, right, of asteroid, right? We don't talk about that. It is called as Kuiper belt, right? Okay. And beyond the Kuiper belt also, there are some tiny bits of asteroids, right? They are, kind of enveloping, right, the whole solar system, right? Bunch of satellites are beyond that as well. So that thing is making up like a cloud, a donut shaped cloud around the solar system. That is called as Oort's cloud, right? So the whole thing is covered in those Oort's cloud, right? So I can show you in some class as well. So there will be a lot of interesting 3D images, right? So go on the internet and try to search about the Oort's cloud, right? Generally we stop at Neptune and we say Pluto is also not a part, but beyond Pluto there is a Kuiper belt. A lot of asteroids are there, right? So Halley's comet and all are coming from that Kuiper belt. It is not from this Kuiper belt, right? It is from that it is not from this asteroid belt that we have near the Mars. No, it is from that Kuiper belt, right? So that is why in so many years you see 1 times that Halley's comet and all. So you see that beyond the Oort cloud, you don't have much influence of sun's gravitational field, right? Yes or no? You don't have much interaction of sun's gravitational field. Okay, Nicholas, right? Namaskar, beta, Om. Okay, so I hope that it is very, very clear. So the gravitational field is region of influence surrounding a mass where the other masses can experience the gravitational force. That is the gravitational field. I hope that is very, very clear, right? The region of influence around a certain mass, right? Beyond that region, you will not be able to interact with this mass, right? So gravitational field intensity. Okay, so whenever we talk about this term, gravitational field intensity at a certain place inside the gravitational field. So first of all, this is the mass and we are well within the gravitational field of this mass. So what will be the gravitational field intensity over here? What will be the intensity over here? What will be the intensity over here, right? So clearly, by common sense, we can say the gravitational field intensity will be higher as we get closer. But what is gravitational field intensity? How will you define it mathematically? So to define and calculate the gravitational field intensity at any place inside the gravitational field, you will place a unit mass over here. You will place a unit mass over here. And the force acting on the unit mass inside any point of the gravitational field is the gravitational field intensity over there, right? The force acting on the unit mass, right, over here is the gravitational field intensity at this particular place, right? I hope the idea is very, very clear. Okay. All right. So how will you measure the gravitational field intensity at any place? You will imagine a unit mass of 1 kilogram and you will see how much force, how many newtons is acting on that unit mass over here. So whatever Newton force is acting over here is the gravitational field intensity at this place. Whatever force is acting on the unit mass over here is the gravitational field intensity over here. Whatever force is acting on the unit mass over here is the gravitational field intensity over here, right? So force acting per unit mass, gravitational field force acting per unit mass at that point, right? So what will be the gravitational field intensity at a distance r? Right? Imagine a mass m is there. So the force experienced by this mass over here is going to be gmm upon r square, right? We divide this entire force per unit mass. Force per unit mass is the gravitational field intensity over here. So gravitational field intensity over here, Ig you can call it. So this cancel out. It is Fm upon r square, right? So yeah. You can also call it Eg, that is also clear, right? Eg is intensity of gravitational field is F upon m, force per unit mass, as I said. So it is going to be this, all right, Gm over r square. Gm1 m2 upon r square. Why did I write down Fm? Gm over r square, sorry, right? So let's keep on moving and talk about the next idea. Okay, so this is the next idea, gravitational field intensity we have discussed. right? Again, it's a vector quantity. Force per unit mass is again a vector quantity, right? Force itself is a vector, so force per unit mass is also another vector, right? So principle of superposition, again, principle of superposition is also very, very clear that intensity of gravitation, if you have to figure out, which is a vector quantity. So there are a lot of masses, they all are creating the gravitational field, right? So at this place, the gravitational field intensity is due to all the masses, right? So due to this one, it is in this direction, due to this one, it is in this direction, and due to this one, it is in this direction. Because the gravitational force is also always attractive in nature. So if you add up all the gravitational field intensities, the net intensity can be figured out over here, right? Right. Okay. Now, with this principle of superposition, you can tell that why the Jupiter is saving us, you can say. You know that this is our sun, and this is Mercury, this is Venus, and this is Earth, slightly bigger, this is Mars, almost same as Earth, and this is Jupiter. So it's not as big as sun, but it is many times bigger than Earth, almost thousand Earth, more than 1000 Earth you can fit inside the Jupiter. Jupiter is huge, right? So since it is huge, it is heavy, it has higher pulling power, right? It has higher gravitational force, right? So between the Mars and Jupiter, between the Michael Jackson, there is a belt. Michael Jackson is wearing a belt. The name of the belt is asteroid belt, right? So you see that this is Earth. Now, if this Jupiter was not there, right? Some of these asteroids will get attracted toward Mars, some of these asteroids will get attracted toward Earth, right? And there will be constant asteroids falling on Earth, and there will be meteor shower on Earth, right? So on one fine day you are sipping tea on your roof, and instead of hailstorm you have asteroid storm coming, all a meteor shower is all over your head. So you don't want that. So you see that this Jupiter is saving you from all that trouble. Why so? Because from the asteroid belt, this Jupiter is pulling all these things toward itself, right? And Jupiter is a gaseous cushion, lot of gases, because it has so high gravitational forces. So the atmospheric gases are very close to the surface of Jupiter, which is why the surface of Jupiter looks like all the gases are on the surface, lying on the surface itself, right? So yeah, very dense atmosphere there is in the Jupiter because of very huge gravitational forces. So yeah, so you see that Jupiter is saving us by attracting those asteroids toward itself, but rarely does that happen that we get the meteor on Earth, right? Rarely that happens, right? So yeah, this is the main idea. Okay, all right. So this is the main idea. Now why I'm telling you this? I'm telling you this because if you talk about any random asteroid in the asteroid belt, it is experiencing the gravitational field due to this thing, due to Jupiter, due to Mars, and due to Earth, right? But the net gravitational field is higher towards the Jupiter, which is why it moves there, right? And not towards it, right? So principle of superposition is acting on that particular asteroid living in the asteroid belt, right? Okay. So point of zero intensity. So you see that this is mass m1, this is mass m2. Where will you have a point of zero intensity? So the point where there is no net force, right, is zero intensity. So of course it is going to be somewhere in between them, right? Somewhere in between these two objects, right? So you see that. So if the point is outside, so what will happen? This is going to attract the object point, and the second mass is also going to attract it. So both of these values are going to add up, so in the same direction. So here you will not get the zero value, right? And similarly, if the point is taken out in this direction, so here again this object is attracting and the other object is also attracting it, right? Because the mass always pull attractive force, right? So again the net value will not be zero over here as well. But if you put in between them somewhere here, so here this one is pulling and this one is pulling in this direction. So again here we can say that the net will be zero, right? Net will be zero. All right. So let's keep on moving and talk about the next ideas. All right. So gravitational field intensity we have calculated, and now let's keep on moving and talk about the next idea. Right. So once we have understood the gravitational field intensity of due to a certain mass, right? Now we can talk about different mass distribution, right? So far we were talking about point masses, and even if we had a spherical mass like planet, right, we used to assume the entire mass is located at the center, right? We measured all the distance from the center for that reason, right? But it is possible that the distribution of mass is slightly different. It is not like a sphere, it is like a ring or some other shape. So what will be the gravitational field intensity due to ring over here? So we will talk about the gravitational field intensity due to the small section, and then we will integrate to find out the net field intensity due to the entire thing. So what will be the gravitational field intensity due to the entire ring? So this is a small section we have taken, dm, and length is dl. So at this place, the gravitational field is acting in this direction, right? At this particular point, we will imagine a unit mass. It is attracted in this direction. The intensity is dE. dE means the fractional due to this fraction. That's why this d in this direction, right? So we can say that this intensity can have two components, right? Two components. Now, just opposite to this mass, we can take another mass of same dm mass and same length dl. It will again pull it in this direction, right? It will have two components, one over here and another over here. You see that against this we have another mass, and the vertical component of intensities are cancelling out and horizontal components are adding up. We can think about two masses like this and that again. So we can say that these two are also going to do the same thing, right? Again, this and this will do the same thing. We can say that the vertical components are again going to cancel out due to these. Again, this one and this one, which are opposite to each other, will cancel out the vertical components again and only add up in the horizontal direction. So clearly we can say, due to all the components, if you keep adding up, the vertical component will cancel out and they will be only horizontal component, right? Okay. So this is how it is happening. Okay. All right. So the effective value in the effective value of intensity of gravitational field intensity around the ring is going to vary like this, right? So just put that in the formulas and you will get this kind of variation, right? For the spherical shell, similar kind of variation you will get, right? Okay, let's keep on talking about the next idea. The next idea is about the gravitational potential. The next idea is about the gravitational potential, right? Okay, so I'm trying to cover up all the concepts mainly, right? Om Prakash. Primarily we are focused on the conceptual part, right? If we can cover all the concepts today, that will be more than enough to address the bridge course, the purpose of this course, right? The purpose of this particular lecture is because it's not a very marathon kind lecture, right? So the purpose of this lecture was anyway to give you the idea of the concepts, right? So that when we are going to discuss it in the 12th grade topics, the concept itself is not going to become a hindrance, right? Solving 2-3 problems is not going to address anything, or the basic level problems are directly formula based. So solving those problems will simply increase the duration of lecture without giving you any true value, right? Okay. So let's continue and keep on moving. Okay. All right. So gravitational potential difference. So when we talk about the word potential difference or the word potential itself, it is related to work, right? The word potential itself is related to what? Work. Okay. It's a scalar thing. So you see that this is a mass, there will be gravitational field around this mass, right? Okay. Now inside the gravitational field, right, let's say that you are trying to move another mass of, let's say, unit mass from one point to another point inside the gravitational field. So whenever you are moving one mass, this is the gravitational field of Earth, right? This is the Earth surface, right? And I'm trying to move this from this point to another point inside the gravitational field of Earth. So I'll be doing some work, right? So the whatever work I have done per unit mass to move up per unit mass to move it from one point to another point inside the gravitational field is the potential difference between those 2 points. Listen it one more time, right? Here inside the gravitational field, if I'm moving the mass from here to here, I have done some work. So work done in this journey per unit mass is the potential difference between these 2 points. Okay, work done inside the gravitational field, right? Inside a gravitational field of any given mass, the potential difference between 2 points is defined as work done per unit mass to move work done per unit mass to move it from one point to another point, right? Okay, so potential difference between A and B, right? Let's say you are moving from here to here. So potential difference between A and B, work done by the external force to move it from this point to this point per unit mass, work done per unit mass, right? Okay. All right. Let's keep on moving. When we talk about the intensity now, so we have already discussed that intensity was a scalar thing, vector thing, sorry, and the potential was a scalar quantity, right? So that's what we have discussed so far, right? And here we are. So here we are trying to calculate the gravitational potential. So let's do that, right? Okay. So you see, in the calculation of gravitational potential, right, there are certain concepts that you have to be very clear with. If the object is moving from point A to point B, right, under the influence of force F, and if force F is constant, then the displacement D, if the displacement is D, we can call the work done by that force is going to be Fd or Fd cos theta. If it was a constant force, Fd cos theta. But if the force is a variable force, we cannot do the same thing. We will try to integrate and find a new value of work done, right? How will you do that? We will say that it is Gm1m2 integral of, how am I doing that? We can say that it is Fx dx, right? Fx ds, this is the value of work done from x initial position to final position, from initial position to final position, right? This is going to be the value of work done. I hope the idea is very, very clear, right? Okay. Okay. Brizikin is saying we need image in 8K Ultra HD. Okay. All right. He has spammed it for a long time, right? Shan is talking about something else. Anyways, no doubt is meaningful over here. So here it is. So let's talk about this idea. So now think about it. If I try to explain you over here, like why we are doing this, what we are doing, right? You see, if you are imagining a unit mass that we are trying to move, the force experienced by the unit mass as it moves is not going to be same. It will experience a variable force. Right now, this is the mass, right? Imagine the unit mass, we are moving from here to here, right? We are trying to calculate the potential difference between this point and this point, right? Think about the force acting right now, which is displacing it from A to B, right? How much work is done by this force? We are trying to calculate that. So the work done per unit mass, which is the potential difference, can be calculated, right? Now, to know that, to calculate the work done, how will you do? You see that the force over here is one value. The distance now is reduced. The force has changed. Distance is reduced. The force has changed. Distance has reduced. The force has changed. So in this journey, the force is variable. In this displacement, during this displacement, the force is variable. It is changing consistently, right? Since the force is a variable force, in this journey, the force is a variable force. So what can we get from this idea? In this journey, the force is a variable force, so we can get that. We can clearly say that the work done by a variable force will be integral of Fx dx, right? That's what we have done over here, right? So the value of force is Gm1m2 by x square, right? And we are moving it from certain place to another place for displacement d, right? So let's say that we are moving from infinity to a certain point. So this is going to be the limits, right? So how much work will be done? Right, in this situation, how much work will be done if you integrate it? So this is how you will calculate how much work will be done. Just a second. Yeah. So you see that the value of potential comes out to be, if after integration, the work done comes out to be this gmm upon r square, and the work done per unit mass is the potential difference between those 2 points. So work done per unit mass is this thing, gm divided by mass, m and m will cancel out. So gm over r is the potential of a certain point, right? How will you define potential of point P, right? Whatever work you have done to take a body of take a unit mass from infinity to that point, right, is the potential of that point, right? So it is gm over r, right? So m is the capital mass which is creating the gravitational field, r is the distance at which we are trying to calculate the potential. So potential at this point is work done to take it from infinity to that point, right? Work done per unit mass to take it from infinity to that point, right? Okay, so gm upon r. Okay, all right. So as you can see over here, we can calculate the potential like this. So it is, of course, you will not be able to remember all these formulas right now, but that is not the goal. The goal is we can calculate the potential due to any distribution of mass, because again, the gravitational force is a variable force, so we have to use integration and all. Don't get confused about that use of integration and everything. In the main batches, I will explain you the basic mathematics, like why we integrate and all those things. We do that, right? We are going to do that. No problem with that, right? So when like if I will be planning a basic mathematics class in 11th grade kids as well, like if you're going for Arjuna batch, and I will be planning a basic mathematics class for the Lakshya batch kids as well, right? So be very clear that if you are in grade 12th, you don't have to worry about anything, right? You will get the basic mathematics class, so you will understand that why are we integrating, why for the variable force we integrate, why we do all those things, right? Those parts will be covered very easily. Okay, yeah. So here we are calculating the gravitational potential because of this mass distribution, right? And we are comparing it with the charge distribution, right? We will talk about a ring, a charged ring, and we will try to calculate the potential over here due to that charged ring, right? So we will do that, right? So this comparison we won't be able to do if you have zero idea about the gravitational potential, right? So right now you have some idea of gravitational potential, I believe. I don't expect that you will get all the clarity right now, but that was not the goal, right? The goal is to explain you the basic concepts, right? What is gravitational potential, right? So yeah. Now you see that the gravitational potential energy, right? Again, a very basic quantity, okay? As I said, the gravitational field is a conservative force. To conserve means to be able to save something, right? So we can say that by definition, we know that gravitational field is a conservative force. That means the work done by this force is independent of path taken. So if you are moving from this point to this point along this path, or you move along this path, as long as the initial and final points are same, we can say that the work done will be same. So work done by the conservative force like the gravitational force is path independent, is same in this path, and the work done is also same in this path, right? This was by definition, the definition of conservative force. But what we can say as well is the conservative force, in a conservative force, the energy, the work done by the conservative force is not wasted, or work done again by these forces in these fields is not wasted, right? For example, I am working while I'm pulling this mass from this place to this place. I have invested some of my energy, I'm not getting that energy back, right? But that energy is stored in the system, right? Earth is there and the ball is there. So this is earth and ball system, right? Earth is creating a gravitational field, and I'm moving this ball from this point to this point inside the gravitational field. So when this ball is over here, whatever work I had done is not wasted, it is stored in this ball, right? And as soon as I release it, it will drop down, it will fall back like this. Yes or no? Okay. So energy possessed or acquired by an object due to the change in the position when it is present, present in a gravitational field, right? So this is the gravitational potential energy, right? So gravitational potential energy is basically the energy is stored, right? Energy is stored due to a certain position inside the field. For example, this is a reference plane that we are taking right now, right? And if an object is placed over here, you do nothing, right? Object will cover the displacement from this point to this point as it is released. You are not working, right? The system is working. The system of earth and object, the energy is stored in this system, and now that energy is doing some work, right? So this energy is the ability of a body to do some work, right? You are not working, so how the work is being done, how this displacement is happening, right? The work is happening because you can see that the work is happening. Why? Because the displacement is happening, the body is displacing, right? So why the body is displacing? Because the energy is already stored in the body, and as it moves like this, right, you see that the potential energy drops and the kinetic energy rises. Over here body has a lot of kinetic energy, due to which it has a lot of velocity, kinetic energy. It rises up all the way over here, right? And again you see that its potential energy rises again, and it drops over here again, it continues to move. So in this journey, the potential energy is dropping, kinetic energy is rising, potential energy is rising, kinetic energy is dropping, and again kinetic energy is rising, potential energy is dropping, like this, right? Okay, but the total energy, if the we can say, if there is no friction, the total energy is going to remain same, right? Okay, the total energy is going to remain same. Let's keep on moving and talk about the next idea. So potential energy is the only defined for a system of masses. Okay, so as I said, potential energy is the energy stored in a system, right? This particular mass is creating a gravitational field around itself. It will not store any energy in itself, right? But inside the gravitational field of this mass, if I take another object and I try to move it in that, right, if I try to do some work, so in that system a potential energy can be defined, right? So yeah, potential energy is always defined for a system. It is stored in the system, right? Okay, energy is not stored in the ball, energy is stored in the system of earth and the ball, right? Gravitational potential energy, initial configuration and final configuration. Okay, so initially the objects were here, then the objects move closer. So now for example, the object is over here and now it is getting closer to earth, so the system has lesser potential energy right now. So the difference of potential energy due to this movement is this thing, work done by the conservative forces. So we can say that how much difference of potential energy has been created. Right now the body is at a certain height from the surface of earth, it is reducing by some amount, so now the body has lesser potential energy now. Hello, hello, hello. Am I audible right now? Physics, Nath, Om Prakash. Hello, hello. Am I audible right now? Okay. All right. So let's keep on moving and talk about the next part, right? From the last 5 minutes, I was not audible. Okay. No worries. So I was explaining you about the gravitational potential energy, right? Gravitation, let me explain you again, right? No worries about that part. Okay. So what was the last point? You can hear me. So you see that we were talking about, I was explaining you the idea of gravitational potential energy, right? I was explaining you the idea of gravitational potential energy, right? So I said that it is the energy stored in the system. It is the energy stored in the system, okay? Right. So you see that this is Earth. Here you have Earth. This is the object. If you take the object from here to here, right, you have done some work. But whatever work you have done is not wasted, right? Whatever work you have done is not wasted. It is stored in the Earth body system. In the system of these two objects, one object is Earth, second object is this body, right? In this system of these two bodies, the energy, whatever work I have done now, is that energy, that work is stored over here in the form of potential energy, right? So the gravitational potential energy is the energy stored in the gravitational field, right? Or you can say energy stored in a system of two objects lying in the gravitational field, right? Okay. Okay. So gravitational potential energy is never about a single object. A single object like Earth cannot have a gravitational potential energy, right? Earth and this object, the pair has some potential energy, right? Earth and this much heavier spool of wire has some potential energy, right? Okay. Okay. Then I showed you this example. If you were not able to hear it, I believe I can show that example one more time, right? All right. So when we try to calculate the gravitational potential energy over here at a height h, it comes out to be mgh. All right. The gravitational potential energy at a height h comes out to be mg into h, right? Talk in Hindi. Come on. All right. So let's continue to move on forward. Relation between Eg, gravitational field intensity and the gravitational potential, right? V. So we are trying to relate these two things, right? We are trying to relate these two things. How can you relate it? Okay, we are trying to relate these two things, right? So how will you relate it? My dear kids, in the chapter of electrostatics, you will see that we are relating the electric field intensity and electric potential. Similarly, here we are relating the gravitational field intensity and gravitational potential, right? How will you do that? So here you see that between 2 points A and B, if a mass is moving like this, right? So mass will move from a place of higher potential to a place of lower potential like this, right? So these 2 points have a difference in potential. Think about it. This is Earth, right? And this is the object, right? Object of mass m, right? At the same height, there is another point B, right? Is there any tendency in the object to move from here to here? We can say that there is no tendency to move from here and here, from here to here, but the object automatically wants to move in this direction, right? Because the gravity is pulling it, because the system has stored some energy in it, and that energy, due to that, this work is being done, right? So we can say that it can move from the place of this place to that place because there is a difference of potential between these 2 points. So objects want to move from a place of higher potential to a place of lower potential, right? So objects can move because of potential difference, as obvious as it sounds, right? Okay. And of course, because of potential difference, what is created? A gravitational field is created, right? Because 2 points have a difference of gravitational potential, what happens? A gravitational field is created, right? And how will you relate them, right? How will you relate them? So clearly we can say that this relation, right, the intensity of gravitation is equals to gradient, like dv by dr. Intensity of this is equals to dv by dr. Intensity of gravitational force, intensity of gravitation is equals to minus dv over dr, right? Okay. If you want to write down this term in a layman term, you can write it down in this way: delta v equals to E into delta r, right? Delta r. Okay. In some books, they are writing that 2 points are at a distance d apart from each other, right? There is a gravitational field of intensity E between them. The gravitational potential between them is V. What will be the relation between them? So we can say that the gravitational potential between them is equals to the gravitational field intensity between them into the separation between them, right? Learning is V is equals to E into D, with, right? Learning is equals to V is equals to E into D, with, right? Simple. So let's keep on moving. All right. So gravitational potential of spheres, we can calculate Gm over r, right? Gravitational potential of a sphere, right now you can calculate Gm over r, right? And at different points, the intensity of gravitation will be different. Okay. All right. So outside it is Gm over r, right? Okay. All right. So again, gravitational potential, when I will teach you the first chapter, we will try to relate it with the electric potential as well, right? So now the next thing is called as escape velocity. Now the next thing is called as escape velocity, right? Let's say that this is our lovely India, right? And now we want to understand the escape velocity on the surface of Earth, right? How will you talk about that? Let's have a look at that. Sir, will you provide the notes? Yes, I will provide you the notes. Like, I took a decent time to make all these notes. You will get it. So this is Earth. This is the object that we have on the surface of Earth, right? And now think about it. If you launch it, right? If you throw the object, right? The object will go to a certain height and then it will fall back, right? If you launch it at a much higher velocity, it will go to another place, another height, and it will again fall back, right? Keep on doing that. If you launch it with a velocity, if you launch it with so much velocity that it is launched, right? This is the gravitational field of Earth, right? Why the object is coming back? Because you are not throwing it hard enough. Object stays within the gravitational field of Earth and it comes back, right? Object comes back. Why? Because it is still in the gravitational field of Earth. It is still in the gravitational field of Earth. That is why the object comes back, right? Okay. So if we talk about the escape velocity, so that means if you are launching it with such a velocity that it escapes, right? And it goes outside the gravitational field of Earth, right? If you launch an object at such a velocity that it escapes and it goes outside the gravitational field of Earth, we call that velocity at which you have launched it, so that it has launched itself into outside a space outside the gravitational field. So it is never going to come back, right? As long as the object is in the gravitational field, it is always going to fall back. But if you have launched it at such a higher velocity that it is rising up and up and up and up, and it is crossing the gravitational gravitational field of Earth itself, right? So the Earth will not be able to pull it because the object is outside the gravitational field, right? So it won't be able to pull it. So we can say that velocity is called as escape velocity, right? Okay. So this, you see that this is a cannon. You are launching it with a lesser velocity. So Earth is round. The object is going to fall like this at some place, right? Okay. This is the cannon and object is going to fall like this. You launch it at much higher velocity, object will fall much further, right? So you keep on launching, you launch it at a much higher velocity. You see that the object has a tendency to, you see that, move. It is consistently falling like this, right? Okay, you see that it has now completed an orbit. Okay, right? So when will an object complete an orbit? You see, object is trying to fall back like this, object is trying to fall back like this, object is trying to fall back on at some other place, because the shape of the earth is round. You see that if the earth was like this, okay, so the object will fall over here, but there was no earth. So what happens? Object continues to fall, right? And when the object continues to fall, it completes an orbit around it. So when the object is making an orbit now, basically we have given it at such a velocity like this so that it can complete an orbit. So right, so now what you have done is you have launched it at a much higher velocity. So now it is happening like this. All right, so you see that this blue circle, light blue circle, is the gravitational field of Earth. So if you launch it at a much higher velocity, instead of orbiting, it will simply cross the gravitational field of Earth, right? It will simply cross the gravitational field of Earth and it will never come back, right? So you see that velocity is called as escape velocity, right? So you are launching it velocity vi. The object is initially at a height h. So this body that is being launched has two energies, potential and kinetic. Okay, so the total energy at infinity, how much energy the object has at infinity? Infinity means any point outside the gravitational field of that Earth, right? So total energy at infinity is mvf square plus 0. So potential energy is not there, right? Potential energy is only there as long as two objects are interacting, right? When the objects are not interacting with each other, there is no concept of potential energy. Right now, the Earth can interact with this ball. So right now we can talk about the potential energy of Earth, potential energy of the system at different separations, right? But we cannot talk about the potential energy itself, right? Where will you get the class notes? My dear kids, don't get worried about the class notes. There is a WhatsApp channel for this particular thing, right? You will get your notes on that WhatsApp channel as well, right? And if you don't get it on WhatsApp channel, we will be providing it on the description of this app, this particular video itself, right? So don't be worried about that. Sir, KSET exam physics will try, right? I believe there is another channel for Karnataka, right? So we'll be trying to cover the KSET exam physics over there as well, right? So don't get again worried about any of those things. So the total energy at infinity. So my dear kids, at any place, the total energy is zero. Total energy is kinetic energy plus potential energy, right? So you see that at infinity, there is no potential energy because the object is outside the gravitational field, right? So the potential energy over here is zero. When the object reaches at infinity, let's say the velocity that is still there in the object is Vf. So this is the kinetic energy that will still be there in the object, right? So this is the total energy at infinity, right? This is the total energy at the point of launching, right? So you see that in the entire journey, the total energy remains the same, right? So once we equate them, right? Once you equate them, this is the condition you will get, right? So that the object is going to go outside the gravitational field. For minimum possible values, this value should be either greater than 0 or for minimum values, it will be equals to 0, right? If you are launching it at a velocity vi, so that this product is, summation is greater than 0. So clearly the object will go away outside the gravitational field and it will move with a certain velocity vf. But again, if it is equals to 0, the object will just move out of the gravitational field and stay there, right? Because the total energy beyond at infinity is 0, right? Okay, so for that, the velocity at which you are launching is only the escape velocity, right? So once you equate it, it will come out to be this root 2 gm upon h plus re, root 2 gm upon h plus re, Okay, all right. So now let's talk about the next idea. क्या चल रहा है? Anyways, चलो क्लास के बाद देखते हैं. ठीक है. So escape velocity we have understood. Let's move on and talk about the next part. Now, for the Earth we have calculated the escape velocity. For the Earth we have calculated the escape velocity. We can also calculate the escape velocity for any other planet. So these are the formulas that we came up with for the escape velocity on Earth. Here you are using mass and radius of Earth. You can calculate the escape velocity on Earth, right? If you use mass and radius of other planet, you can get the escape velocity on that planet. Clear? So it is these parameters, right? The geometry of the planet, it is basically geometry and the radius of the planet. Radius means geometry, right? And mass is mass, right? So these things will decide the escape velocity on any other planet, right? So for Earth, put mass of Earth and radius of Earth, it comes out to be 11.2 kilometers per second. So if the cannon is launching it at 11.2 kilometers per second, object will just cross the gravitational field and stay there. It has no kinetic energy left. All the energy will be wasted to just cross the gravitational field, right? If you're launching it higher than that, it will remain some of the kinetic energy, it will cross it and then it will move as well, right? Okay. Object thrown from surface, okay. All right. Maximum height attained by the body. So what will be the maximum height attained by the body? So clearly you can say that for the maximum height, the final velocity will become 0 over here, right? So apply the third equation or equation of motion. When you apply it, you can calculate the, maximum height attained by the body, which is this. Not very useful, right? Now at last we have to talk about the Kepler's law, right? Now what is really happening? What is really happening? In the beginning, we used to think that, like church used to think that in the Europe, that the entire universe is created for us human beings. The God has created the entire universe for us, and which is why we used to imagine the geocentric model, that the Earth is there and the world is moving around, the universe is revolving around Earth. So sun and other planets and moon and everything is moving around Earth, right? Later on we understood by Copernicus, the dare of Copernicus and all in the Europe. So all the patents and all the theory and all the patents are there on their name, which is why you will not find the Indian scientist name in all those science books, because we could not file patents, right? We didn't know that this thing patenting exists. Anyways, so at that time, what really happened? Copernicus came up forward, and he explained the idea that the world is not, this universe is not made for us, right? We are just a little part of it. So it's not geocentric. We are not at the center of the universe. Maybe we are not even know what is universe, right? So basically, a little portion of universe we can comprehend so far. That is our solar system, right? And we are moving around sun, by the way, right? And little moon is moving around Earth, right? And there are a lot of other moons moving around other planets like Saturn and Jupiter, right? So these things are happening, right? All planets move around sun. But he said that they are moving in a circular orbits. Later on, there was a guy, his name was Kepler, right? So, other than Kepler, there was another guy, his name was Tycho Brahe, right? Search about that Tycho Brahe on the internet, you will find that. He was a rich guy, right? He had so much money, so he bought a little island, right? So that he can do the little research, whatever he can do. At the time, he had a very basic telescope, right? So what he did, he set up a basic observatory of his own. He had an assistant, and the name of the assistant of Tycho Brahe was Kepler, right? So with the help of all the assets that the Tycho Brahe had, right, the Kepler performed, Kepler took the relative measurements of some planet like Mars, right? compared to their stars. So Kepler said that, okay, at this time of the month it was here, at this time of the month it was here, at this time of the month it was here. And by plotting all the values, somehow, right, all the complicated things, right? So after doing all that, he understood that the Mars is not covering same distance in the same span of time. You see that? If something is moving in a circular orbit, right? And there is no force acting on the Mars, right? Nobody is applying force on the Mars to make it move faster or slower, right? So it should always move with the same velocity on a circular orbit, okay? And if it is always moving with the same velocity and you wait for some time, let's say in 10 minutes, Mars is covering some distance, right? At some angles, it is covering some angular displacement. Let us say that 1 degree, right? You wait for 10 days and the angle covered by the Mars, let's say, was 5 degree, okay? Again, you wait for another month and again you give a time span of 10 days again. It should again travel for the same angle. Angular displacement should be same. But Kepler said that the angular displacement is not coming out to be same, right? In July, Mars is covering, let's say, 10 degrees, but in September, right, when Mars is somewhere else and it is covering 15 degree, right? So Mars is not maintaining the same velocity around the sun. So the other planets must be doing the same as well. And for that to happen, the orbits must not be circular, because if it was a circular orbit, it would always have the same velocity. So he came up with the conclusion that all the orbits are slightly elliptical, right? And the further away you get from the sun, it is more elliptical, right? And later on, he came out to be 2, right? So he based on that, based on the motion of the planets around the sun, he came up with 3 explanations, all the data that he was collecting now. He came up with these 3 things, right? Those 3 laws are called as Kepler's laws, right? Backed by data, right? That is why it is so much appreciated, right? Lot of scientific missions are based on his name, right? Kepler's, and lot of observatories are based on his name as well, and a lot of space findings are based on his name as well. Anyways, so Kepler is doing all this, and you see that when you draw an ellipse now, so ellipse does not have one center. Ellipse has 2 foci, for plural of focus is foci, right? So ellipse has 2 foci, and sun is at one of those focus points, right? So you see that the planet is revolving around the sun, around the ellipse, and sun must be at one of the centers of that ellipse, right? Okay, this is how the planet is moving, not in the circular orbit. This is the first law. It is about the orbits. It tells you the orbits are not circular, they are elliptical. It is called as law of orbits, right? So law of orbits, right? And sun is at one of the focal points of the orbit, right? R1, R2, these are unnecessary things written about, the ellipse coordinate geometry. Okay, so the next thing is this, the radius vector. Now, you see, he observed that, as I said, this planet, while it is moving around the sun, is covering certain angle in 1 month, right? In 1 month, it is moving from here to here. So it is covering certain angle, right? Again, in different part of the year, he again waited for 1 month, but the angle covered was not same. Right now, the angle covered, let's say, 60 degree, right, for that 1 month. But for another part, the angle covered was 30 degree, right? It is not same. So you see that, but he said that, okay, the angle covered is not same, but if I do one thing, what? If I join the sun and the planet, this vector you can call it, this particular vector, just radial vector you can say, right? The line joining the sun and planet, right? This line sweeps a certain area na, in 1 month. This line joining sun and planet is sweeping certain area in 1 month, right? And again, this line joining sun and planet is again sweeping certain area in again another part of the year in the same time, 1 month. It is sweeping this much area. He came up to a conclusion that these areas are same. Very weird stuff, right? He said that the angles are not same, but the area swept by the line in the same time, the area swept by the line joining sun and planet in the same time is exactly the same, right? He called that aerial velocity. right? He called that aerial velocity, the area swept by the line joining the sun and planet, right? Okay. And he said that aerial velocity, area covered per unit time, A1 upon T1 is same as A2 upon T2, that is constant, right? Area covered by the radius vector per unit time is same, okay? This is the second law, right? So if you try to measure the aerial velocity by using some of the trigonometry thing, right? So you can get that, right? Do the little trigonometry and you can calculate that. Now the next thing is Kepler's third law, which is Kepler's law for the time period. So clearly we can say that the planet which is further away from the sun will take more time to revolve around it. Yes or no? The planet which is further away from the sun will more time to take, one full rotation around the sun, right? It is common sense. But he could clearly relate that he said that the square of the time period and the distance from the sun, they are not directly proportional. It's a very weird relation. He said that the square of time period is proportional to cube of distance from the sun, okay? The square of the time period is proportional to the cube of distance from the sun, okay? Now, one more thing, right? As the planet is moving around the sun, nobody is applying force, push, right? The velocity to change the velocity, right? So what we can say that the velocity, the value of velocity is changing, right? Because of the orbit itself is changing, right? But since the system is isolated, there is no external force on the system. So what will happen? The momentum will remain same, right? So as the planet is moving around the sun, right? Its velocity keeps on changing, but the momentum stays conserved, right? So you see that m1 v1 r1 is same as m2 v2 r2 is same as everything. So as the planet continues to move, its momentum stays the same, right? Now the next thing is called a satellite. By observing the Kepler's laws, right, we can say that the Kepler's laws of planetary motion are applicable for satellites as well, right? The satellites are the objects that move around the planets, right? So it could be natural satellite like moon, it could be artificial satellite, a lot of other artificial satellite like India has Aryabhatta and all, right? So a lot of Indian satellites are there, like IRNS system and there are so many systems these days. PSLVs are the rocket launchers and everything. So Gagan system and everything. So here it is happening. So you see that this is a satellite moving around Earth. This is a satellite moving around Earth, right? We can tell so many things about these satellites, right? Like what will be their orbital velocity and everything. So you see that you are launching a body at a certain velocity, it will fall at some place. You will launch at a higher velocity, it will launch at some other place. But if the velocity is a specific one, right, at the time of launching, it will continuously fall and come back at the same place like this, right? So you see that the orbit will be higher and bigger, right? And it will continuously move in this way, right? So you see, at a certain velocity VA, the object fell on somewhere on the earth following an elliptical trajectory. At a certain velocity, it follows an ellipse and moves around the earth itself. If the velocity of launch is too high, you see that it follows a trajectory around C, which is giving you elliptical orbit. If you launch it at a much higher velocities than that, it can again follow a parabola or hyperbola like this, right? Okay. So orbit of satellite, okay. So this is what we are interested in. The satellite is moving around a planet. What are all the forces acting on the satellite? The centripetal force is acting like this, right? And the object is moving with the velocity, tangential velocity v around it, right? Okay. So if the satellite is moving around a planet of mass capital M in a orbiting radius r, its velocity is governed by it, right? You see that this is the force acting on it, right? And the force, centripetal force, whatever force is acting between them, the gravitational force must provide the required centripetal force because it has to cover a circular orbit, right? So if that is true, right, this gravitational force has to provide the centripetal force, so they must be equal, and by equating them we can get the value of orbital velocity at in a orbiting radius r, which is under root gm upon r. Orbiting radius is r. So if the satellite is at a height h away from the surface of Earth, above the surface of Earth, and radius of Earth itself or planet itself is r, so radius of planet itself is capital R, let's say. So this total distance r will be radius of planet plus height from the surface. Radius of planet plus height from the surface, r plus h, that is a total small r, right? Okay, so this is the value VO, orbital velocity, under root gm upon r. So clearly you can say that in a orbit of radius small r, you can launch a satellite of a smaller mass, a heavier mass, they have a same velocity. You see that? Because the orbital velocity is not dependent on the mass of the satellite itself, it depends on the mass of the planet. But in a certain orbiting radius r, the orbital velocity does not depend on the mass of the satellite, it depends on the capital M, which is mass of the planet itself, right? So all the satellites which are lighter and heavier, they are all moving with the same velocity in a particular orbit, right? Okay. All right. Okay. So the orbiting for Earth, it is 7.9 kilometers per second near the surface of Earth, right? Okay. So we can relate the escape velocity and orbital velocity. We know these relations, right? And if you try to replace it or take the ratio of it, we can say that escape velocity is nearly root 2 times of orbital velocity, right? So if an orbit is, if the satellite is moving in this particular orbit with a certain velocity v naught, how much time will it take to complete one thing? So one rotation. So the time period will be total distance 2 pi r upon v naught. So this will be the time period upon v naught, right? Okay. So if the satellite is revolving very close to the planet surface, if the satellite is very close to the planet surface, then what will happen? If the satellite is revolving very close to the planet surface, then we can say that the orbiting velocity will be around 7.9 or what we have calculated already, right? And the time period will be 2 pi under root r upon g, which is around 84 minutes. And you will find that the International Space Station has a time period of around 90 minutes or so, right? Okay. All right. And what will be the angular momentum of satellite? Once you know the mass of satellite, once you know the velocity of satellite, angular momentum will be mv, which is the linear momentum, into the distance r, right? So when you multiply that, you will get the angular momentum of the satellite is gmm square upon into r, right? So clearly angular momentum of anything depends on its own mass, right? Energy of the satellite. So any satellite has two energies, kinetic and potential. But you see that the satellite, while it is moving with velocity v naught, has a energy this much, kinetic energy this much, gmm upon 2r, positive, because all the values are positive, mass is positive and velocity is squared, so that everything is positive, right? So this much positive energy it has, gmm upon 2r, right? Now the second thing is, potential energy. The potential energy is negative. It tells us that the satellite is bound with another object. That's why the total energy is negative. And total energy, for total energy, just add them up, right? It is minus gmm upon 2r. Negative sign implies that they are bound with each other. That's what I've told you, right? So the binding energy is that total energy that you have calculated, right? So you have to supply this much energy to the system so that you can separate it from one another, right? Okay. So these are the relations for the orbital velocity. These are the basic relations. You can take the screenshot of this thing so that you can revise it. Anyways, you can get the screenshot, you will get the notes of this particular lecture and you can move ahead with it, right? So the types of satellite, there are polar satellite that moves around the poles, right? And the next satellite is, it moves around the poles, and as the Earth rotates, it scans a little band, right? So clearly in every rotation, it only scans a little band. So yeah, it rotates first of all at a very high speed. In 90 minutes, it completes one full rotation. So you cannot cover the entire portion of Earth, a large chunk of Earth, by using polar satellites. So if you want to use it for communication purposes, these are total waste of money. So you have to set up a lot of polar satellites in that case, right? And in that case as well, those will not be able to work. But if you want to have, let's say, a satellite that covers a large chunk of Earth, right, and it stays wherever it is, it rotates with Earth, it is logged with Earth. So for that, you have to launch geostationary satellite, right? So geostationary satellite, right? So for geostationary satellite, you have a certain distance which is around 36,000 kilometers. What we have figured out in this particular orbit, the time period of the satellite is such that it matches up with the time duration of this particular Earth rotating about its own axis, which is 24 hours, right? Time Earth takes to rotate about its own axis 24 hours, right? So Earth is taking 24 hours to rotate about its own axis. Satellite is also taking 24 hours to rotate about this Earth, right? So both of them are together at the same time. So you see that all the time you have a satellite over there. So for the communication systems, it is easy to point somewhere and your signal will come back. All right. All right. So that's pretty much everything, right, about this class. Okay. So I hope we have understood a lot of concepts, right? Lot of concepts in this class, right? We have revised the basic things. And after revising those basic things, we have also seen what happens with satellites, what are Kepler's laws, and as well, we have seen what are the different terms as well, right? So that's it. Let's keep the lecture till here only, and I will see you then in the next class. Till then, take care. Bye-bye.